Hi, this is Julie from Chem 7 at Los Bananas. So this is going to be chapter 5, and we're going to talk about gases, liquids, and solids. So this chapter has quite a bit of math for the gas laws, so we need to get you guys going on that. We're going to talk about 3 states of matter in this class. We've talked about them a little bit before, but now we're going to go in depth. And we're going to talk about when we change from one state of matter to another. So for example, if I take gas, which is like gaseous water, like you feel humidity on a hot day, and you have a nice cold drink on the patio, and you see all those beads of water on the outside of that, that's the gaseous water in vapor changing to a liquid water, and that's called condensation. You guys understand melting and freezing, so that's an easy one. And when you take water and you boil it on the stove, you're vaporizing it from a liquid to a gas. So when it goes in the gas phase and it's like humidity in the air, then it can slow down and condense on the outside of a cold beverage. That's condensation. And you see that on cold winter days when your windows are all fogged up, when you're trying to get to work, when you have to put the defroster on. So that's condensation on your windows from the water in the air, the gas in the air, gaseous water. So another thing is you can take gas and you can cool it really fast and it'll turn into a solid. That's called deposition. So when they they do this in some situations where they'll take a metal, they'll heat it up so hot it turns into a gas, and then they deposit it onto a solid surface. So that's called deposition. So all those shiny helium balloons you see that they're all silvery and stuff, they've been the metal's been heated up and then quickly deposited onto that helium balloon surface, and it's now shiny. So there's metal deposited on top of that balloon. So that's called deposition. And then we can also take a solid and we can heat it up really fast and we can turn it right into a gas. So that's called sublimation. And you see this also for if you take a ice cube out on a really hot day and you see gases coming off of it like still-fix steam. That's actually ice changing directly into a gas. So it's not going through the liquid stage, it's going right from solid into gas. That's called sublimation. So we're going to talk about energy in this chapter and gas laws. So there's a lot of math in this chapter, so we'll get through this. So don't worry, I'll help you get through it. But there's 2 things to know about. When we have that melting point, when water's going from solid to liquid or back from liquid to solid, that's called the heat of fusion. And it's a number. There's a certain number, it's a constant, for every solid and for every solid for any type of material. So it's a particular number that they figured out for all solids. That's called the heat of fusion. So when water goes to liquid, from ice goes to liquid water, then that's a particular amount of heat that we have to use. For water, the melting point is 0 degrees C. When we boil water, that's called the boiling point, and that's 100 degrees C. But there's a particular amount of energy we have to put into that water to make it boil. So that's called the heat of vaporization. And it's a particular number. So those numbers aren't things you have to memorize. I will give them to you. To figure out how much heat we're going to use, we need to know how much mass we're going to take of a particular substance. Like, say I take some ice, I have to weigh it, and that's going to be the M number. And then I have to multiply by that delta H, which is the heat of fusion if I have ice, or it's heat of vaporization if I have water. So I'm just going to take the mass of whatever thing I have, solid, liquid, or gas, and I'm going to multiply it by this delta H. And it's going to give me how much energy I need to do that process. So that's called Q. Q is heat. So Q is a letter we just use for heat. And we can measure it in calories, or we can measure it in joules. Calories or joules. So it just depends on what number you're given right here, what your answer is going to be, what unit you'll have. So you'll either have calories or you'll have joules. So we sometimes give it to you in calories per gram, and that's more usual for health applications, but we might also give it to you in joules per gram, and you'd see that when you go to a physics class. So here's an example. Say I have 2 liters of water, and that weighs 2,000 grams. So you have to remember that 1 milliliter equals 1 gram always for water. And then the delta H for vaporization for going from a liquid to a gas is 540 calories per gram. And all you have to do is multiply those numbers together and you'll get the total number of calories that it would take to make that liquid water vaporize into a gas. So that's the kind of math we do in these problems. It wasn't too bad, you're just multiplying together. Sometimes we're going to have situations where we have a particular phase of matter and we just want to heat it up. And we want to find out how much energy that would take. So this is a little bit different problem. When you see a temperature change, you're going to add that to the problem. You're going to put the delta T, that's called just the change in temperature, times the mass of whatever you're trying to heat up, times the specific heat. So this is the number that you'll be given in the problem. This is a constant. You'll have to figure out how much did the temperature change. That's just the subtraction part. And then the mass is given to you in the problem. So this is really the only thing you have to do. You have to remember, you have to figure out which equation to use. So this is when we see a temperature change. Use this one. And the only thing you have to do is figure out the change in temperature and then multiply all those 3 numbers together. So that's not too bad. So we're going to look at our heating curve when we talk about all this stuff, because that will help us figure out what type of equation we need. So when we're at the straight line, when solids are melting or when liquids turn into a gas, we only use 2 numbers and we multiply them together. The constant and the mass. So when we're on these straight lines, right here, you'll only need 2 numbers to multiply, and you're going to use this equation here, where you have mass and the constant number, the delta H number. Okay, so when we're here, we're only going to use when we're here, we're only going to use 2 numbers. Okay. When we're here, then we have to use that other equation where we have a change in temperature, because this is talking about changing in temperature. So when we have this slope here or here or here, then you've got to use 3 numbers. So this slide kind of tells you that. When we're on the straight lines, we're only going to use 2 numbers. The mass and that constant that you will be given. When we're on those slopes, we've got to figure out that change in temperature, that's the slope part, times the mass, and times this number, which is a constant you'll be given. So the only thing you have to do extra is figure out that change in temperature. So it's not too bad. We just have to remember when to use which equation and what constant to use. So those are the hard parts of this. We'll figure that out. So we'll do practice in class. So let's jump to gases. So particles are really, really far apart. They're always moving. They don't, you don't know how big or small they are because they can take the size of the container they're in. They just move all over the place until they fill whatever container they're in. So they don't have a shape or a volume. It depends on what they're put into. Okay, and gases always bounce around like pool balls on the pool table, where you hit one and it just goes in a straight line. So that's how they move. And how fast they move and how often they hit the sides of the container tells you the pressure of that gas. So pressure is a measurement of how much gas particles are hitting the side, how many are hitting the side, and how hard they're hitting the side. That's gas pressure. So this is just explaining that again. And pressure is how much force those little particles are hitting the side of the container. So how many are hitting and how forcefully they're hitting is how much pressure you have. So our atmosphere presses down on us in all three dimensions around your body, so you don't feel it, but there really is a lot of air above us, way, way, way out into the exosphere. So there's lots of gas particles pressing down on your body. And that pressure at sea level, which is pretty much where we are in Pittsburgh, is 1 atm. 1 atmosphere is the name of that. That's the pressure. That's all the gas particles above you are pressing down on you. And so standard atmospheric pressure is called 1 atm, 1 atmosphere, and at 0 degrees C is called standard temperature and pressure, STP. So this is really important right here. This is just something to memorize. STP is 1 atm at 0 degrees. So atmospheric pressure can vary. Like if you're on top of Mount Everest, it's going to be a lot less pressure on your body because you're way high up and there's less gas particles pushing down from the exosphere all the way through all the layers of the atmosphere down to your body. Okay? We can measure pressure by letting the atmospheric pressure push down on liquid mercury that gets pushed into this glass tube, and that pressure pushes down and then pushes this up. So the higher this goes, the higher the atmospheric pressure is. If it's lower, that means there's less pressure. If it's higher, that means there's more pressure. So we measure atmospheric pressure in a barometer, and sometimes in a lab we use a manometer to figure out the pressure that's happening in a chemical reaction. And you guys will measure blood pressure as well, and that's the pressure that blood is pushing against the arteries and the veins. So pressure is how much the particles are moving, how fast, and how many you have. We're going to be using gas laws when we talk about gases, and there's several gas laws, and we can divide them up into individual called Boyle, Charles, and Avogadros. But it's best if we just use one overall gas law and then just apply it to the situation we're in, so you don't have to memorize so much stuff. Okay? So gas laws are ways of figuring out volume, pressure, temperature, or amount of gas in different situations. So we'll try those. So Boyle's law says that if you increase the pressure of a gas, the volume decreases. And you know that if you took a balloon and pushed it on all sides, you could make the volume a little bit smaller. So that's Boyle's law. And we can use that with math, but I'd rather show you the equation called the combined gas law. So just know that when you press down on gas, you'll increase the pressure. When you warm up gas, you'll increase the pressure, and you'll increase the volume also. So Charles' law says when you warm up a balloon, the volume is going to be bigger. So this is the math for that, but we're going to always use the combined gas law. The thing we have to know for gas laws, though, is that we have to use degrees K. So that's called Kelvin, and it makes the gas laws work out properly. So to do Kelvin, you're just going to take the degrees Celsius, TC, and add 273 to them. So just remember this 273 number, and that will get our math to work out properly. So temperature always has to be in Kelvin. So make sure you know that because that's a common error. So this is the law we should always use, combined gas law, so you don't have to memorize so many things. And we just use whatever's useful in the problem. Sometimes they won't have pressure, so you won't put the pressure numbers in there. Sometimes they won't have volume, so you won't put volume. Sometimes they won't have temperature, so you don't put the temperature. So I'll show you how to do that in class where we figure out what the situation is and how to use this gas law. But let's just remember the combined gas law. That's the most important one. There are also, the more particles you have, the more numbers of moles you have, the bigger the volume as well. That's called Avogadro's law. So the first one I want you to know is the combined gas law. The second one I want you to know is called the ideal gas law. And this is when you're dealing with grams or numbers of moles. So it's called the ideal gas law. And in this also, we have to use degrees K for the temperature. R is a number. I'll always give you that number. So that's a constant. Don't worry about that. I'll always give you that one. N is number of moles. Volume is liters. And pressure is in ATM. It's a unit of pressure. Atmospheres, like we talked about just a little bit ago. Okay, so that's the ideal gas law. So remember the combined gas law and the ideal gas law. Those are the ones that we will use in class. The third and last one is called the Dalton's law of partial pressures. It's very easy. It says if you combine various gases into a container, the pressure is going to be a combination of all of the individual pressures that you have. So if I put in a little bit of oxygen and nitrogen and maybe a few more little ones that we have in the gas that we're breathing right now, if I add all those gas pressures up, I'm going to get the total pressure of what we're feeling on ourselves right now. It's really easy. You just add up all the pressures and get a total. So that one's a really easy law. Let's move on to liquids and solids, new topic. So there's different ways that liquids and solids can be attracted to themselves. So like a water particle to another water particle. We talked about this a little bit with hydrogen bonding. So water has hydrogen bonding going on because we talked about one side's a little negative, one side's a little positive. So they're polar molecules and they like to stick together. Water's very sticky. That's called hydrogen bonding. So anytime you have something with an N hooked to an H or an F hooked to an H or O hooked to an H, you're going to get hydrogen bonding, which makes polar molecules, and they are very sticky. They like to stick together. This is the strongest intermolecular force. All molecules have some London dispersion. This is really, really a weak force, and it's because the electron clouds in molecules move a little bit, and then they start having a slightly positive side and a slightly negative side. It's really, really random and happens a little tiny bit. So London dispersion is weak. And then molecules that have a permanent dipole and another permanent dipole will be strong. Will be the intermediate and stronger than London dispersion forces. So we need to talk about these in class because these get confusing for people. So let's talk about London dispersion, and I will review it in class because some people have trouble with this. So this is the deal. We have two molecules up top here, and they're just hanging out, and then for whatever reason, some of the electrons decide to shift to this side. And so then the molecule is slightly negative on the left side and slightly positive on the right side. That's the sigma things again. Okay, so when that happens, then this guy becomes a little magnet, and it forces this guy to also do the same thing. So then this side becomes negative, slightly negative, and this becomes slightly positive. So this is just happens randomly, and so once it happens, then it makes other molecules around it do the same thing. Okay, so that's called London dispersion forces, and they're temporary. Dipole is when you have a molecule where, remember the little analogy I was saying, one kid is stronger than the other and able to pull a blanket over themselves. So that means that chlorine is stronger and able to pull the electron cloud around itself and off of hydrogen. So this is not very much covered up. This is really covered up well. And that means this side of the molecule is negative, slightly negative, and this side is slightly positive. And then they attract and make other molecules line up with them like magnets have a north and south pole, so then some are attracted to each other, some are repelled, and then they orient themselves so everybody is happy. That's called dipole-dipole forces. Hydrogen bonds are the strongest ones. Remember I said H hooked to an O, H hooked to an F, or H hooked to an N are going to make hydrogen bonds. And these little dots are not real bonds, but they are attractions to each other. So this H is attracted to this O. That's called a hydrogen bond. And it makes water really sticky, makes it able to climb up capillary tubes and things like that. It's really, really special and makes water unique and very helpful in the human body. These are types of solids. We have different types of solids. So some are molecular, for example, and they don't have a lot of intermolecular forces, so they have low melting points and boiling points. So those are molecules. Ionic ones are like sodium chloride, and they really have high melting points and boiling points. It's hard to break them apart. Metals are unique because they have a center of the atom. So like, for example, gold has a nuclei in the middle, and then all the electrons are able to move freely. So I think of it as a sponge. So you've seen copper wire in your house and stuff like that, in a cord, in electrical cords and stuff like that. So copper does this really well. So imagine the nuclei of the copper being like a sponge material, like your kitchen sponge. And then you fill it up with water, and the water, imagine that's like electrons. And so if you have a nice wet filled up sponge with water, that's what metals are like. And then if you squeeze that sponge, the electrons can move, the water can move. That's what happens in copper and metals. The electrons, if you force them, they can move. But the copper stays in one place. So your copper electrical wires, the wire stays in one place, but the electrons are able to move from one place to another. And then the last one is called a network solid, and that's what diamonds are. They have covalently bonded carbon, and they make a really, really tight network, and it's very, very strong. High melting point, highest melting point, highest boiling point. So diamonds, you know, are super strong. So here's how water looks as a solid. It's hooking together by those hydrogen bonds because they're sticky, they like each other. So it makes a nice solid. Sodium chloride is bonded together by the plus-minus attractions. And they're orderly. They have to have one chlorine next to one nitrogen to balance out that charge. And metals are the weirdos. They're like I was just saying, the copper nuclei, the center of the atom, is staying in one place. They're all staying in one place, like the sponge material. And then you fill up the sponge with water, and that's what the electrons are like. They're just in between these nuclei. And then if you push on that sponge, if you squeeze your sponge, the water's going to drain out. Okay, so that's the way metals are. The electrons move if you force them to. And then diamonds are very, very strongly bonded together, covalently bonded. You know covalent bonds are very strong. So that's how, and it's all in 3 dimensions, very, very strongly bonded together. So if we look at bonding, we're going to have, it takes more and more temperature to go from a solid to liquid to a gas. And the higher the molar mass, the higher the melting point and boiling point. The stronger the intermolecular forces, the higher the melting point and boiling point. So I keep saying that water's sticky. So water, you see here, is all in 3 dimensions attracted to each other, and it's very, very sticky. So that's why water scooters can float on top of water, because their legs don't go through the water, because water likes to stick to itself. It doesn't want to stick to that bug. And that's it for this chapter, so I'm hoping we can get through the math without too much pain, and I will help you make it as easy as we can possibly make it. Alright, have a great day. Thanks for listening.